the next presentation is from Andrei Zhukov. If Andrei or any other presenters are there, please share your screen. Unfortunately, I cannot find you on the participants list. Okay. So Nikolay Bolotnik. Okay, good. Good. So the next presentation is titled "A Walking Robot with Thermomechanical Actuators for the Inspection of Photoelectric Cells of Solar Arrays for Spacecraft." I think the presenter is Nikolay Bolotnik. So Nikolay, you can continue.
I'm a presenter, thank you. Dear colleagues, we wish to share with you our ideas and concepts related to robotic inspection of the panels of solar arrays on spacecraft. At the present time, the technical state of solar arrays, say on International Space Station, is monitored by fixed sensors. These sensors are not located on the panels of the solar array, and they usually measure integral electrical characteristics of the operation of the entire solar array. If the sensors show deterioration in the operating parameters, its array should be inspected for failures. The location and character of the failures are not known in advance. In this case, the inspection works have to be produced by astronauts outside the station, which increases the life and health risk for the astronauts. In the International Space Station, solar array has an overall area of 2,400 square meters and consists of 4 modules of an area of 600 square meters each. So the inspection of these modules is time-consuming and labor-consuming task. The operating failures of the solar arrays are frequently caused by cracks due to collisions of micro-meteorites with photoelectric transducers. On the slides, you see a panel of a solar array from Mir space station. Mir is a Soviet space station that is not operated now and even does not exist. Of course, the photoelectric transducers are covered with strong glasses, and the collision with micrometeorites are rare events. However, space stations are operated for many years and even for decades, and for this time the micro damages can accumulate to the level that destroys the functional integrity of the photocells. Our idea is to equip the space station with a kit of cheap mobile mini or micro robots that could crawl over the modules in order to locate the failure and transmit the relevant information to the crew. To develop such micro robots, one should analyze the structure of the solar array and the factors that deteriorate the operating parameters, analyze the inspection techniques available for solar arrays, analyze the achievements of mini-robotics, in particular in space robotics, propose a design schematic for a mini-robot and analyze its locomotion principles and possibilities, and perform a feasibility analysis of the proposed engineering solution. The state-of-the-art in space micro-robotics is presented diagrammatically on this slide. We do not have enough time for a detailed survey of research and development in this field. We will say only that the respective studies are carried out virtually in all countries that have their own aerospace industry or use spacecraft and satellites for implementing practical tasks. These countries involve, in particular, China, France, Germany, Korea, Russia, Sweden, Japan, United States of America. To our knowledge, the task of robotic inspection of solar arrays has not been considered so far, and the space robots that have been developed and designed previously, in our opinion, do not fit to this task. First of all, for technological reasons. We suggest a working robot based on thermomechanical microactuators that serve at the same time as drive and legs. Each actuator is a biomorph structure, is a biomorph silicon polyimide structure. It consists of the silicon base that has V-shaped notches filled with polyimide. The beam has electric conducting buses on the bottom face. When an electric current is passed through the buses, the entire structure is heated. Since the thermal expansion coefficient of silicon is substantially less than that of polyimide, the actuator bends. When unheated, the actuator has a curved structure, has a curved shape. When heated, it straightens. The degree of straightening depends on the temperature. Thus, by changing the temperature, we can control the shape of the legs due to which the robot can walk. On the next slide, the experimental physical model of the micro-robot is shown. I want to say that this photo is significantly magnified, and the robot is questioned. Its linear dimension is about 1 centimeter. Maybe for inspection of solar arrays, the dimension of the robot could be larger. Here you see the platform and the legs, mechanical legs. Such a robot can move along a straight line or change its rotation, its orientation, but rotation if the legs work, if the legs are working in antiphase. Here is the experimental prototype, and on this slide you can see this prototype in action. This experiment were produced not in space but on Earth under gravity conditions. When in space, there is no gravity, and an important issue is to provide a reliable contact of the foot of the leg with the underlying surface. We suggest to use dry adhesive materials to adhere the foot to the underlying surface. When getting adhered, the foot approach the surface perpendicularly to it, and when detaching, the leg contains also thermomechanical revolute joint, and when detaching, revolute joint is engaged, and the foot detaches with formation of a crack that propagates along the interface. Such mode of detection requires considerably less power than detachment along the perpendicular. This flow chart demonstrates the sequence of stages for one step of the progressive motion of the robot. At the beginning of the step, all actuators are heated, and the robot lies on stretched legs. The feet of the right legs are adhered, and the feet of the left legs are detached from it. Then the right actuators are cooled and bent, and the robotic platform elevates over the surface and gets a forward displacement. By repeating similar motion, we can organize a periodic gait of the robot to move along a straight line. We have defined the operating requirements for the micro-robot, which can be used for inspection of the solar arrays. I am not about to dwell in details on this characteristic. I can tell you only that these requirements take into account the space conditions, in particular the radiation, weightlessness, vacuum, temperatures, and so on. And we have developed an algorithm of motion of the robot. I want to tell that the structure of this robot somewhat differs from the structure of the robot shown on this slide. Here we have only legs parallel to one of the legs arranged in one direction, and on the robot that is suitable for inspection of solar arrays, it's better to equip the robot with another set of legs, which are arranged along the transverse side. And here it is shown an algorithm for scanning of the scanning of the solar panel for inspection. And in this slide, schematically, a conceptual model of the micro-robot for inspection of the solar arrays is shown. You see the platform with thermomechanical legs, and these cubes show the equipment with which the robot should be endowed. I would like to say that despite the legs are very tiny, this robot can move a relatively massive load, because it operates in weightlessness, and the weight of the load will not damage these legs. So we think that our proposal can be this type of the robot can be considered as a candidate for inspection robot for solar arrays. Now, brief conclusions. A concept of the inspection micro-robot for operation in space is suggested. The problems that need a solution for the engineering implementation of the robot are defined. The task of the creation of micro-robot that is able to operate in space needs a multidisciplinary approach. A significant part of scientific and technological foundation for creating a prototype of the space micro-robot have been created. To complete the task, specialists from various branches of science and technology should be involved in the project. Thank you very much for your attention.
Thank you, Professor Bolotnik, for the interesting talk. I invite audience to ask questions.
Yes, hi everyone. Can you hear me?
Yes, I'm here.
Hello, good morning. Thank you
Morning.
thank you, Nikolay, for your great presentation. It's very interesting. I would like just to know if you had the chance already to test this micro-robot in microgravity environment.
Uh, we are thinking about it. We are thinking about an experiment on in International Space Station.
Okay.
But we are not ready to start these experiments right now. Now we are now we are testing, now we are working on the structure of the robot, or on the design of the robot, and the major issue for us to make this robot autonomous, to enable it to operate without wires, and still we use wires with our experiments. And as to experiments in microgravity, I am repeating, we are thinking about this, and maybe we will make such experiments maybe even before completing wireless version. But of course, in this case, these experiments will be performed inside the space station, not outside. But nevertheless, microgravity is inside us.
Okay, or even in a flight, for example, inside a Falcon plane with parabolas and.
It is possible, but frankly speaking, we did not think about this.
Okay, thank you so much.
Thank you very much for your question.
Thank you, and congratulations for your research.
Thank you.
Thank you, Professor Bolotnik.